In this example, we are going to conduct a series of equilibrium analyses to find something. Right? So let's look at what we're supposed to do. System of 4 cables, 1, 2, 3, 4, suspends a 1,000-pound bank of lights. We don't see the lights, but we see the effect of the lights on the system, so 1,000 pounds, above a movie set. Determine the tension in cables AB. All right, let's mark these that we're after. There's AB, and CD, it's over here, and CE. Those are the 3 things that we're supposed to find. Determine the tension of the cables AB, CD, CE. AB is 45-degree orientation with respect to the horizontal. So let's carefully get that marked in here. So 45 degrees. There we go, right there, 45 degrees. And AC is 30 degrees with respect to the horizontal. Don't know if we need all that information because that's a member that we're not asked to find, but we'll get it jotted down as a given. Alright, so, interesting. Well, let's make sure that we really understand what we're about. Alright, so, given a cable system, as shown in this case, and so what we're going to find is we're going to find the tension in AB, tension in CD, and tension in CE due to the applied load. Right now, our applied load is right here. And these 3 things are called internal forces. Internal forces are in reaction to the applied load. Alright, the way we're going to do this, of course, is with our basic primary tools that we'll use throughout statics, 2 of them, free body diagrams, and from that free body diagram we will write equations of equilibrium over and over and over. Alright, so what we're going to do here is try to figure out how we start. Interesting. So we know we can do free body diagrams. We've got equations of equilibrium. Those basic equations are going to be sum of forces in the x equal to 0, sum of forces in the y equal to 0. So 2 equations. Well, now wait a minute. If we only have 2 equations, I can only have 2 unknowns at any one time. So we might be able to string a bunch of things together to make a system of equations, but there's some limits here about what we can do. So, what I do know is that we've got cables, and cables are always in tension. So let me go down and consider starting where we have the applied load, and let's cut around that joint. So we'll start with, then, as our step number 1, sorry, you got to get the right color out. Step 1 is going to be the free body diagram of joint A. Right, this is exactly the way I want you to do this in the homework in terms of documenting your work. Right? Label, number, steps, underline the label, or you can bubble it if you prefer. Here's joint A. Now it doesn't matter how close we go to joint A, but we don't want to be, we can't go through the joint, but we can get pretty close. If you want, you could show the short little stubs of the cable, but don't take that out very far. We're going to be pretty close. We would say technically it's infinitesimally close to the joint, but not through the joint itself. You can't cut through a point, because a point is, by mathematical definition, doesn't have actually any real width. And then we're going to show the force that we got here, also at 1,000 pounds. Right? That number symbol is also a symbol for pounds. Right? Now remember, the line of action of the force is the same as the straight line between the 2 ends of the cable, especially for the work that we're going to do now. Later on we'll talk about how to handle the self-weight of the cable. Cables are in tension, so they're pulling away from the free body. Away, away, away. There's some sort of song that could go with that. Just sounds like, away, 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 away. So here we are. TAB. Doesn't matter for now what the order of the subscripts is. That just is associated with that rope or cable AB. Here's this other one, TAC. Now, we weren't asked for TAC, so I'd rather not calculate it if we don't have to. But nonetheless, it's showing up in the free body diagram. But look, two unknowns. We know their orientation, so actually we could solve for those two, and we have a whole variety of ways that we could do this. We could do it through the scalar equations that are the equations of equilibrium written down in that kind of form, or we could do it in reality as a force triangle. Right? I'm going to do it as a scalar equation this time, and for the next one we're going to actually do it using a triangle, and you'll see why that was so clever to do. But we could use a force triangle and do law of sines, law of cosines, or we could do it as a system of scalar equations. Now, let's start. We do them one at a time. Let's start with x. We have two different sign conventions. One about how we might handle the way we've done the free body diagram, and we do all our math and we find out that TAB is negative. Well, negative means opposite of, and so that would just mean that if we ended up with a value, numerical value for TAB of a negative number, that meant the force is in the wrong direction. We need to switch it. Now that would also mean that the force or the cable is in compression, and that would actually indicate a problem in our model somehow, that a cable went into compression. That's not a good thing. So we hope we get positive numbers here for all these. Now then there's the sign convention about the equation. I have to decide, do I want to take in the equation things to the left as positive or things to the right? Everybody always wants to take to the right positive, and I want to show you it doesn't matter. So I'm going to take to the left positive, and then what I got to do is get all the scalar components of in this case the x component. So I come down, you can create a little right triangle, and okay, we got TAB, its x component is heading to the left. That's my positive in my equation, so that would be TAB cosine of 45 degrees. And then we've got the x component for AC going in the other direction, so that's minus TAC times cosine of 30 degrees is going to be then set equal to 0. I didn't include the 1,000 pounds. I don't even have to write it in because cosine of 90 degrees would be 0. There is no x component to the 1,000 pounds. Right? Notice the x component of AB has to equal and be opposite of the x component of AC in order for there to be equilibrium in the horizontal direction. Right? And so since I don't really want TAC anyways for now, we'll solve this for TAC. TAC equals then, let's see, it goes the other side. We have TAB cosine of 45 degrees over cosine of 30 degrees, and I don't know what that is. Let's just calculate it real fast. 45 cosine divided by 30 cosine equals 0.816, and I'm going to keep one more digit because we usually round things to 3 or 4 anyways, and that just kind of gets that hanging in there, times, of course, TAB. Right, now, I was being clever. I looked ahead, and I noticed if I sum forces in the y, and once again, just to illustrate how we could do this, I'm not going to either. I'm going to do it just like you probably are going to do it. Take upwards positive. And so I'll have a plus TAB. I need the opposite of my angle for that vertical component, so that's sine of 45 degrees. And then plus TAC, and I want opposite of the 30, so that's sine of 30 degrees. And then minus 1,000 equals 0. I'm going to set that equal to 0 right there. Right? So note what we get out of that equation is that the sum of these two has to be equal to 1,000, and of course we'll have 0.707 TAB plus 0.5 TAC, sine of 30 degrees is 1/2, is equal to 1,000. Now I know that TAC is equal to 0.8165 TAB. So I can put that in there and factor out some things here. There's your TAB equals 1,000 pounds. Right? Let's go ahead and get the 1,000 pounds in there. And so now let's see what we've got. Plus it's 1.115 TAB equals 1,000 pounds times 1,000. And so TAB is equal to 896.6 pounds. Wow, that's pretty big. That's a large fraction of 1,000 pounds. Wow. Okay. So I'm going to take that now times 45 cosine. So the x component was 634 pounds. And because it's at 45 degrees, so will the y component be 634 pounds. So of this 1,000, more of it gets split over to AB, because of course AB is more vertical than what AC is. Right now, I might not even care about what TAC is. I happen to know we're going to need it, and so I'm going to go ahead and calculate it. That TAC equals 0.8165 TAB. Notice the positive, by the way. That means this was acting just the way we thought it would. Oops. Yeah, I got to do all the math again now. Plus 0.5 times. And why not just use the 896.6? Because I want to keep the resolution that I had without any rounding errors. There's that 890, and then we take that times 0.8165. Now there's a rounding error in there, just a tiny bit. But TAC would equal a plus 732 pounds, and that's going to be, of course, in tension also. All right, so there's our 2. Now what we do is we go up to joint C, and we then do the same kind of thing where we're going to do a free body diagram of joint C, see what we can get. Notice we've got 1, 2, 3 things there, 2 that we want. All 3 were initially unknown, but now we know AC. So, hey, I got 2 equations, 2 unknowns, and so when I go do this, I know I'm going to be able to solve for things because now I know AC. So I did need to find AC, at least right now. And I say at least right now because in reality, there's another way that we could have done this, but we haven't introduced formally the concept of a moment of a force and the equilibrium equation associated with moments. Once we do that, we'll actually have an alternative path to do this work, and so we can come back to that later. Alright, so cables again. So they're pulling away from the free body diagram. Well, the vertical is TCD, the horizontal is TCE, and then we get TAC. Now, I want to point out something crucial. TAC is pulling away from the joint, but hey, wait a minute. Up here, it was going in the other direction. Right? These are internal forces. The free body diagram that we did not show was that of the member itself. Right? So let me show the cable, and if I'm going to show that intention, then it's got to be pulling away and pulling away. And notice what's going to happen. If we were to paste this back together vectorially, these 2 are going to disappear. And in the original structure, well, there is no cut. Right? So in the original structure, you can't see that force. It's internal. That's what it means to be internal, inside the member. And if you don't cut the member, you can't expose it. Right? And so at one end of the member, we've got it pulling away. At the other end of the member, it's pulling away. They're in different directions, even though they're have the same meaning. And the final thing that people really just don't quite get and are uncomfortable with is when you cut something and remove something, on what's left, you got to show the effect of what you removed, not the other way around. I'm not trying to say what this joint does. I'm trying to say what does this member do to that joint. So they usually want to draw this force going upwards right when you need the force that going lower left. That's usually the mistake that people are making. Right, now, we could do the same sum of forces of the x and the y. I don't want to do that. I'm going to do the force triangle method, which says take each of the three forces and draw them to a reasonable scale. And so I know that TAC is 732 and change. It turns out to be 732.1 pounds. Right? And it's at 30 degrees. And then I know that TCE has a line of action that is horizontal. And I know that TCD has a line of action that's vertical. And what that tells me is I started up here at the tail of the TAC, drew 732 at 30 degrees. Let's get that in there. Boom. And then I've got TCE going to the right, and where it intersects with the line of action with the vertical, then I know it ends, because then I have to have one going up that gets me back to the original place. So there's your TCE, there's your TCD. And that's your force triangle. Now this is a very convenient force triangle because we have two orthogonal components. I designed the problem specifically to do this for us. Alright, so this makes it actually pretty easy. This is our statement of equilibrium right there for that joint. And so now it becomes very straightforward. TCE is going to be equal to 732.1 times the cosine of 30 degrees, which is root 3 over 2, right? Cosine 0.866. And that will be, whoa, I got 845. That's not right. It can't go up. That's times 30 cosine. There we go. 634.0 pounds. And then TCD, and it's plus, means we got it in the right direction here. You can tell that just by the way we set up the arrows and go back to the beginning. And that's going to be 732.1 times sine of 30 degrees, which of course is 1/2 of that. That's 366.06, which we always take that. Oh no, we don't either. It's not a 5, it's a 0, so that goes to 0.1 for now. And so what's my final answer? Well, my final answer is going to be the following, that we have TAB, which we wanted, at 896.6, doesn't start with a 1, so we're going to round up to 897 pounds, of course in tension. We have TCD equal to 366 pounds. Remember that last little decimal is to say that's not exact to 366. And then we've got the final one, TCE equals, did I get those backwards? No, I did. That's CD, CE is up above, 634 pounds in tension. Right? And those are your answers for this system of cables that support a bank of lights above a movie set.